Hello, everybody. Just getting a few things together here. Okay. All right, let's see what's going on. Sorry, let's see. Okay. Posted a quiz for you guys. You should work on that when you have a chance. No big hurry though. It's due Wednesday at 1 a.m. I think. Here is both the attendance and the tutoring link in case you're interested. One of my students from my 17A class was saying she has used the tutoring and she found it very helpful. So if you're looking for extra help, that is one place to get it. Have any of you guys used it? It's okay if you haven't. I'm just curious. Use it if you want to. It's definitely there for you. I've got some examples of some nonlinear differential equations I think we should go through, but if there's other things you guys want to talk, well, just to sorry, let me fix something here real quick. I did see that Rademacher started talking about probability stuff, which we will definitely get to, but I don't think today is the day for that. Although if you really don't want to talk about other things, I guess we could. But I was going to do some nonlinear differential equations and yeah, kind of go through the whole spiel. So hopefully these aren't too terrible. I came up with them on my own. I think they're all right.
James, is the quiz week 6 quiz posted yet? Or
So. Is it not showing up on Canvas?
I checked files and the only thing I see is quiz 5. I don't see quiz 6.
I thought I put it up. Let me check real quick here. I know I wrote it. Did I post it? Sorry, it's not actually there. One sec. Sorry. Let's see. Yeah, I really thought I did that last night. Oh well, sometimes you forget you do the things you think you do. Or vice versa. There we go. Okay, it should be now in the usual place where, it probably also is in files, but if you click on assignments and go to quiz 6, it should be there. Sorry about that. Okay, so let us look at a couple examples of classifying the equilibria of nonlinear differential equations. And so I'm planning on doing it using the Jacobian matrix. We can also talk about the graphical method. But personally, I think the Jacobian matrix is easier to understand and easier to work with. But we can also talk about the graphical stuff. So we'll have to talk about some of the graphical stuff. Let's see here. Patterns, yeah. So what have we got? We've got the following differential equations. We've got dx dt equal to, let's write it this way, y squared minus 4xy plus x squared y. And we've got dy dt equal to, sure, 6 minus 3x minus 2y plus xy. And since we know we're going to be using the Jacobian matrix, it does make sense for us to think of, oh yeah, this is going to be our function f as a function of x and y. This is going to be g as a function of x and y. So later on, we're finding the Jacobi matrix, which is just the matrix of partials fx, fy, gx, gy. right? So it's good to kind of make sure you know what things are before we get going here. So where to start? I guess we want to start by finding the equilibrium points. So I'm going to start by, so again, finding the equilibrium set is finding where both differential equations are equal to 0 at the same time. So let's set the first one equal to 0. Now, I would imagine most of the time, some of the factoring that's going to happen might actually already get done for you. Well, let's factor. So here I've got, I can factor on a y. So I'm left with y equal to 0, or this whole equation equal to 0. So I see this equal to 0 as y equal to 4x minus x squared. And all of this is going to be okay. So now I'm going to go into my other equation and try and substitute these things in to figure out. So this seems like it might get difficult. So if I plug in here, if I plug in y equals 0, let's see. So I'm going to get 6 minus 3x minus 2y plus xy equals 0, 0. So I'm going to get x equal to 2. All right, so I've got one equilibrium at 2, 0. And I don't think I get anything else by plugging in y equal to 0. So let's try plugging in y equal to 4x minus x. Now that seems like it's going to get kind of terrible. I actually don't know what's going to happen because I did this a different way. But let's see what happens. So if I plug in y equal to 4x minus x squared, I'm going to get, let's see, 6 minus 3x minus 2 times 4x minus x squared plus x times 4x minus x squared. Equal to 0. Okay, I know where this is going to go, but it's not pretty. Yeah. Okay, so this definitely factors by grouping. So if I look at this here, I can think of this as x minus 2 times 4x minus x squared. And I can think of this as negative 3 times x minus 2. And then I can factor out the x minus 2 and get x minus 2 times 4x minus x squared minus 3. Wow, that's kind of weird. And so then I got to factor this some more. You get x minus 2. This is I'm even terrible at factoring like this. Let's see, minus x. I think it's a minus 3 and a plus 1. That gives me a plus x plus 3x is plus 4x. Yeah, that works. All right. So by plugging in y equals 4x minus x squared, I ended up getting x equal to 2, negative 1, sorry, positive 1, right? Or positive 3. And then I plug back in here to find the corresponding values. So if x is 2, I would get y equal to 8 minus 4, which is 4. If x is 1, I get 4 minus 1, which is 3. If x is 3, I get 12 minus 9, which is 3. All right. So here are my 4 equilibria. They are 2, 0. And there are these 3 points, 2, 4, 1, 3, 3, 3. All right, let's talk about this in a different way, because although this is fine, this isn't really how I imagined it in the first place. So here's where these equations came from. I guess I can erase some of this. This algebra isn't super important. So the way I really imagined this equation was this here. This is, what is it? 3, sorry, where'd you go? Yeah. 2 minus x times 3 minus y. And this, not surprisingly, is just y times y minus 4x plus x squared. And so now it's a little bit easier to see, like this, what kind of null lines we have. In fact, I want to graph the null lines. So it is certainly possible, although sometimes algebraically challenging, to find equilibria just by solving the systems of equations, right? Seeing where one thing is equal to 0 and then plugging that condition into the other. So, right, so we definitely said, oh, y is 0, plug in 0 over here, see what you get. And then we said this part's 0, plug that in over here and see what you get. And it happened to work out okay here. Sometimes it works out terribly. But you can also graph the null lines. And if we do that, let's see what we get. And so let's be color coordinated here. Let's follow that. So I said, yeah, we'll do red for this, blue for this. Okay, so my x null lines are going to be y equals 0, which is the x-axis, and also going to be y minus 4x plus x squared equal to 0. But that's just y equal to 4x minus x squared. It's a downward opening parabola with intercepts at 0 and at 4. So it's going to look like sorry, I feel like I'm making a dumb mistake here. Let me think about something for just one sec. Okay, sorry, I'm being silly. I was plotting the points wrong there. Okay. So again, these are the x null lines. Right, so if you were to draw the direction field anywhere on these red lines, the arrows would be either pointing straight up or straight down, because dx dt is 0 on each of these red curves. Similarly, the y null lines are pretty easy, right? I'm setting each of these equal to 0. So I'm going to get 3 minus y equals 0 gives me y equals 3. 2 minus x equals 0 gives me x equals 2. So here's x equals 2. Here's y equals 3. And so I can see my 4 equilibria. Right, we have one here at 2, 4. We have one here at 3, 1. Sorry, 1, 3. We have one here at negative 1, 3. And we have one here at 2, 0. And that's it. Those are all the null lines, right? Or sorry, all the equilibria, which are exactly the ones we found over here. Just to be super clear, we don't have one here where the two like null lines intersect, and we don't have one here or here. Right? You only have equilibria where the different types of null lines intersect each other. Okay. We don't need this picture, but it is a nice picture to have, and we might come back to it. So, yeah. Let's go ahead and find the Jacobian matrix. And this is definitely when I think we prefer to have it multiplied out. So I would much rather have dx dt equal to y squared minus 4xy plus x squared y, and dy dt equal to 6 minus 3x minus 2y plus xy. Yeah, because if you write it in the factored form, then taking the partial derivative is going to require the product rule, which is just, I mean, it's not impossible, it's just a little more work. So I think it's worth it to multiply it out before you start partial differentiating. Also, in case you missed it, here's the attendance one more time. Attendance and tutoring link. So let's find the Jacobian matrix. Again, it's just fx, fy, gx, gy. So let's see. Partial of, so again, and this is f, this is g. So the partial of f with respect to x is 0 minus 4y plus 2xy. And the partial of f with respect to y is 2y minus 4x plus x squared. And the partial of g with respect to x is negative 3 plus y. And the partial of g with respect to y is negative 2 plus x. So that's our Jacobian matrix. And then we're going to plug in each of the equilibria to then see what kind of stability or instability you have. So let's go ahead and plug in 2, 4, just to start with. So I plug in 2, 4. Let's just write it this way. Let's be realistic, James. So that's going to equal, okay, I gotta be careful. So plugging in 2 for x and 4 for y. I'm going to get negative 16 plus 2 times 2 times 4 is 16, so I get 0. And then I'm going to plug in 4, so 8 minus 8 plus 4. And then negative 3 plus 4 is 1. And then negative 2 plus 2 is 0. Okay, so here is the matrix. The trace is 0. The determinant is negative 4. We could find the eigenvalues, but we don't have to, right? I can see from this knowledge here that I am definitely in the saddle part of my graph. Right, so this means we have a saddle. In fact, whenever your determinant's negative, you're always going to have a saddle. Sorry, yeah. But we could also find the eigenvalues, right? The eigenvalues, if you were actually going to find them, you would be finding the determinant of this matrix here. So it'd be, this matrix minus the lambda I, so negative lambda 4. But you would just get exactly a lambda squared minus 4, which gives you lambda equal to plus or minus 2. And we know that that gives us a saddle when the eigenvalues are opposite values. But it's always going to be true that if your determinant's negative, you're already there in the saddle place. So you can stop here or you can do more work. All right, so let's go ahead and figure out what's happening at, let's say, what's the other ones? 1, 3? Sure, 1, 3. So again, so it is a little bit messy to plug it in. We have to be a little bit careful. Let's go ahead and do it. So let's see, 3 for y, 1 for x. So negative 12 plus 2 times 1 times 3 is 6, and negative 12 plus 6 is negative 6. And then let's see, 6 minus 4 is 2, plus 1 is 3. And then negative 3 plus 3 is 0. Oh, so getting that 0 there makes me really happy because I know that my eigenvalues are just going to be the diagonal entries. So that's great. Negative 2 plus 1 is negative 1. So here I know my eigenvalues are both negative, so I know I have a sink or a stable node. Okay. I can probably erase some of this. I don't need this right now. So why don't you guys find the Jacobian at 2, 0. Right, go ahead and find that, and then also classify for yourself what the eigenvalue, what the stability is. All right, anyone want to volunteer what they think the stability looks like here? While I dance around. We could find the eigenvalues. When these zeros are here, the eigenvalues are super easy, right? You just, the determinant of your matrix is going to be lambda squared minus the product there. You can get lambda squared minus 12 equal to 0. Because, right, you're just putting in a negative lambda, that minus that, So you get plus or minus root 12. And again, we have real eigenvalues that are opposite signs, so we have a saddle once again. You also could have known that just by knowing the determinant was negative 12. So I have a saddle here. And then for the last one at 3, 3, right? It was 3, 3. No. Yes? Am I dumb? I am dumb. I mean, not really, but yeah. Yeah, I had the wrong value on my for some reason. I had negative 1, 3 for some crazy reason. I plug in 3, 3. So I'm going to, let's see, negative 12 plus 6 times 3 is negative 12 plus 18, which is 6. And then plugging 3, 3 here, I get 6 plus, 6 minus 12 is negative 6 plus 9 is 3. And here I get 0, and here I get 1. So it looks like I have eigenvalues that are 6 and 1. So I have an unstable node or a source. So that's what's going on there. If you guys want, well, even if you don't want, I'm going to show you anyway. We can look at P-plane here for just a second. So here's the graph for this system of differential equations, or the direction field, I should say. And we can see, right, so we've got the equilibria at 2, 4, so over 2, up 4. So right here, we have a saddle, right? At 2, 4, we have a saddle. Yeah. And we can see that if we pick some points around it, right, again, it's only a saddle kind of near that, but we're definitely kind of going in towards it and then moving away. Definitely looking very saddly. And then we can see over here and over here, we definitely have our nodes at 1, 3, and 3, 3, an unstable node at 3, 3, and a stable node at 1, 3. So over here at 1, 3, we can see, oh yeah, things are definitely pointing into that. Wow, this is kind of a cool graph I came up with here. Whereas over here at 3, 3, things are going away from the node. And then finally, we have, what's the last one we had? Sorry. 2, 0. So over here at 2, 0, we should have a saddle as well. And we definitely do. You don't even have to click things, right? You can totally see these arrows going this way, these arrows going that way, right? We definitely have a saddle-y kind of thing going on. It's a cool graph I came up with, just kind of accidentally. It's got a lot, there's definitely some symmetry to it, which is kind of neat. So that's definitely what that looks like. What else do I want to say? So let me ask you guys, should we talk at all about the graphical method where we do the things where we kind of draw some arrows on our phase plane? I'm happy to talk about it. I'm happy to skip it though if you guys don't really need to see it. Who votes yes? Go ahead and do it. Cool. All right, I think we should do one more. And so here's what I'll say. The way I presented this one in the first place, I think was kind of, I don't think anyone would give you one like that unfactored the way I gave it to you in the first place. Right? That just doesn't seem very typical to me. So let's look at this next one. Let me give it to you in the way. Yeah, this one seems okay. So here, and I've made these, I feel like maybe more challenging than they need to be, but not really. I was trying to tell them the things that look interesting. So let's say we've got dx dt equal to, so this one I am going to not factor because the factoring is actually really easy. X squared plus 3xy minus 11x, and dy dt is going to be, this one we are going to factor, it's y minus x minus 1 times 2y minus x plus 1. Even though we don't have to graph the null lines, I think it's worthwhile. So let's go ahead and graph these null lines. So this one I said was easy to factor, and it is. Each of these has an x. So this is looking like x times x plus 3y minus 11. So here are my null lines so far. I'm going to have x, well, not so far, altogether. X equals 0 or x plus 3y minus 11 equal to 0. Those are, remember, the null lines. And my blue null lines are obviously going to be y minus x minus 1 equal to 0 and 2y minus x plus 1 equal to 0. And all of these are looking like they're lines. Typically, when I'm graphing a null line, I do want to try and isolate y, right? Because we're used to graphing y as a function of x. So here, I'm really thinking of this as y equal to x plus 1. And here, I'm thinking of this as, let's see, 2y equals x minus 1. So y equals 1/2 x minus 1. And here in red, solving for y is a little less nice. I've got 3y equal to negative x plus 11. So y is negative, let's do a negative 1/3 x plus 11 thirds. And so now I can kind of get a better handle on graphing these things. So let's see. Here's my x-axis. My y-axis I'm going to draw in red because my y-axis is one of my null lines. Or isofine if you prefer that language. So let's see. So I'm graphing y equal to x plus 1. I'm graphing y equal to 1/2 times x minus 1. So I have an x-intercept at 1, a y-intercept at negative 1/2. So it's something like this. And I'm not trying to be super precise here. And then let's see. I have a x equals 0 already. And then I have y equals negative 1/3 x plus 11 thirds. So it's going to start up here somewhere and do something like this. So without any solving, I can see that I have 1, 2, 3, 4 equilibria. Okay. Let's go ahead and try and find them. These two should be really easy to find because they're just on the line x equal to 0. Let's go ahead and find those first. So, what you're really doing, right, is you're saying, okay, I'm going to pick this, and then I'm going to plug that into that to figure out what y has to be. So, right, so if I'm saying x equals 0, I plug that in there, then dy dt equals y minus 1 times 2y plus 1 equal to 0. So I either get y equal to 1 or 2y plus 1 equals 0, so y equals negative 1/2. So not surprisingly, I get 0, 1, and 0, negative 1/2. Which is exactly those points there. And the same thing, but now instead of setting x equal to 0, I'm going to set this equal to 0. I'm going to plug that in. Now, yeah. Let's see, am I kind of out of room? Oh, maybe. Sure. So this is why I think graphing it is nice. Because really I can tell I'm just trying to figure out where this line x plus 1 and this line, which I just erased, which was y equal to negative 1/3 x plus 11 thirds. I'm really just trying to figure out where these two things intersect. And the same thing for this red line and this other blue line. Y equal to 1/2 x minus 1. So I could go through the work of taking this and then plugging it in for y here and y here, and then setting the whole thing equal to 0. But really I just know I'm just going to find where this line, this line, this line. So I'm really just going to set these two parts equal to each other, which I will say is equivalent to plugging this in for y here and then setting that part equal to 0. But I think it's nicer just to do this. So I'm going to say, okay, that equals that. So 1/2 times, I'm going to multiply that. So 1/2 times x minus 1/2 equals negative 1/3 x plus 11/3. Let's not deal with the fractions. Let's multiply everything by 6. So I've got 2x minus 6. Let's try that again. Okay, 3x minus 3 equal to 6 times negative 1/3 is negative 2x, and 6 times 11/3 is 2 times 11, which is 22. So then add x over here, right, 2x, you get 5x, add 3 over here, you get x equals 5. And if x is 5, y is going to be negative 5/3 plus 11/3, which is 6/3, which is 2. So that point there is 5, 2. So we're getting and 5, 2. Why don't you guys find this one over here by setting y equal to x plus 1 equal to y equal to negative 1/3 x plus 11/3 and see what you get for that. So I got 2, 3. What else do I want to say about that? Not a whole lot. One thing I will say is you can definitely check, right? If you plug in any of these for equilibria, both of the differential equations should be simultaneously 0. Right, so if I plug in 0 for x and 1 for y, plugging in 0 for x here definitely makes this 0. Plugging in 0 for x and 1 for y makes this part 0, which makes the whole thing 0. Same deal for 0 and negative 1/2. You're plugging 0 for x, that's 0. You're plugging 0 and negative 1/2. 0 for x and negative 1/2 for y. I get negative 1 minus 0 plus 1. So this part is 0 here. So that one checks out, that one checks out. 5 for x and 2 for y, that's a little more work. So if I plug in 5 for x, I'll get 5 there. 5 for x and 2 for y, I get 5 plus 6 minus 11, which is 0. 5 for x and 2 for y. Here doesn't help, but here it does, right? Because I get 4 minus 5 plus 1, which is 0. So every pair of points you plug in should make both of them equal to 0. That's the whole idea when you're finding equilibrium. I guess we should go ahead and now classify them, right? Because I don't know what's happening here. So let's take a look and see. So let's go ahead and find the Jacobian. So for the Jacobian, that is where you're going to want, I think, I don't know, let's talk about it actually. So here's my dx/dt, x squared plus 3xy minus 11x. And here's my dy/dt, which is y minus x minus 1 times 2y minus x plus 1. So partial of this with respect to x, 2x plus 3y minus 11. Partial of this with respect to y, 3x. Partial of this with respect to x. I mean, I feel like the particle is just going to suck here, right? Like, I don't want to do -1 times this plus this times -1. That just seems lame. So I think I'd rather multiply this out, even though it's going to kind of suck. So multiplying it out, you get 2y squared minus xy plus y. You get minus 2xy plus x squared minus x. And then you get minus 1 times each thing, so you get a minus 2y plus x minus 1. And the x's do cancel, and you could group things together and say it's 2y squared minus xy minus 2xy minus 3xy plus y. So let's say I've dealt with this, I've dealt with this and this and this. Oh, sorry, but minus 2y gives you a minus y. And then plus x squared minus 1. Double check that's what I got. Yeah, okay. So I personally think multiplying it out is better here because then taking the partial is not terrible. Right, the partial with respect to x is going to be minus 3y plus 2x. And the partial with respect to y is going to be 4y minus 3x minus 1. So do what you will. I think this is better. All right, now we have to find the Jacobian at each of our equilibria, which were 0, 1, 0, negative 1/2, 2, 3, and 5, 2. That seem right? Yep, okay. So we're just going to plug in each of those. So let's see what we get. So J01 is going to be, okay, 3 minus 11 is negative 8. 0, that's exciting. Negative 3, and let's see, 4 minus 0 minus 1 is 3. All right, what do we have? Our equilibrium is a so I see a new message. Sorry, I thought my chat didn't say anything. Yeah, saddle. Thank you guys. Yeah, exactly. Because our eigenvalues are easy to see, right? They're negative and positive, so we know we have a saddle. Saddle, our lambdas are negative 8 and positive 3. Okay, let's look at 0, negative 1/2, because that will probably also not suck. So let's see. So if I was doing 0, negative 1/2, I would totally look at the fact that this is going to be 0. So I don't even have to figure out what's down here, right? It doesn't matter what's down here because I already know my eigenvalues are going to do this and all these. So I would ignore this completely, even though it's not hard, and just do that. So let's say make it 0 minus 3/2 minus 11/2 is negative. I don't even care if it's negative or positive or what number it is. Down here, I get negative 1/2 times 4 is negative 2 minus 0 minus 1 is also negative. So I know I have a stable node or a sink because my eigenvalues are both negative. But I didn't even bother finding them. I just knew that since I had a 0 here, I could only pay attention to their signs, which is kind of nice. All right. Let's go ahead and find saddle, sink. Let's do the other two, which will probably be a little bit more complicated. So let's do 2, 3. So let's see what we get here. So 4 plus 9 is 13, minus 11 is 2. You have to be careful with your arithmetic here, right? It'd be easy to make a mistake. 3 times 2 is 6. I bet this is going to be 0. No, it's not. Negative 9 plus 4 is negative 5. And 12 minus 6 minus 1 is 5. Okay, I don't know, so we have to do the work. So again, if I want to do it kind of what I think is the fast way, I see that my trace is 7. I see that my determinant is 10 minus 30, which is 40, right? That's going to be 7 plus or minus the square root of 7 squared minus 4 times 40 all over. So that means it's going to be, this is clearly negative inside here. Right? The square root of 49 minus 160. So we have imaginary eigenvalues. Our real part's positive, which means we have an unstable spiral. Which way is it spiraling? Clockwise. So I wrote myself a little note down here that when you have a spiral, meaning when they are imaginary, if this one's positive and this one's negative, then it's clockwise. And if this one's negative and this one's positive, then it's counterclockwise. And really, I would just write myself a note because that's the only way I'm going to remember it. All right, let's look at, so it's going clockwise.
So instead of finding the eigenvalues for that, could we just have used tau and delta and use that graph that we did on Friday?
Definitely, because here, so yeah, so let's actually talk about that. Because here you could definitely say, okay, we have that, right? So we're comparing tau with, oh gosh, sorry, it's what is it, tau squared over 4? Yeah, so delta is 40, which is bigger than tau squared over 4, right? Which is 49 over 4. And right, so since you're bigger, right, you're in that top part of the, above the parabola part, and you're on the right-hand side because tau is positive. And that's definitely the part where you are, I mean, I don't have the picture on right now. That's definitely the part where you are in unstable spiral, where you're above the parabola, right? Left side is stable, right side is unstable. And then if you're above the parabola, you are spiraling. If you're below the parabola, but still above the x-axis, you are sourcing or sinking. Noding, you're a node. And then if you're way below, you're a saddle. Yes, so yes, you can totally use that graph. Let's look at this last one here. So if we plug in 5 and 2, let's see, we're going to get, okay, 10 plus 6 is 16 minus 11 is 5. And then 15, and then negative 6 plus 10 is 4. And then here we're going to get 4, right? 8 minus 15 is negative 7. Okay, so here's something I know just looking at this. Since these are the same sign, it's not going to be imaginary. It's not going to be a spiral. Right? These have to be opposite sides to have a spiraling, unstable or stable spiral. So here we can do the same thing, right? So actually, so let's look at our trace. It's negative 3. Our delta is negative 40 minus 60, which is negative 100. And in fact, we don't even need the trace here. Knowing that delta is negative means we have a saddle. And the reason why this is happening, just to kind of be more explicit, right? In this case here, our eigenvalues look like this. It'd be negative 3 plus or minus the square root of negative 3 squared minus 4 times negative 100. And here's the deal. When this is negative, negative 4 times it is positive. And so whatever this number is, it's a bigger in absolute value number than this number here. And so you've got something, doesn't matter if it's negative or positive, if you're adding and subtracting something that's bigger than it, one thing will be positive and one thing will be negative, which means it has to be a saddle. So that's why when delta is negative, you always get a saddle, because this square root thing here is a number that's further from 0 than this trace number here. And so you always get something negative plus something, okay, it's gonna plus something big enough to make it positive, and then minus something that will still make it negative. And it's true, whether or not this is negative or positive for the trace. All right, so let's go ahead, since we have a few minutes, let's go ahead and look at what the p-plane, I mean, we don't need to look at p-plane at all. I just think it's fun. I'm not gonna lie. I think the p-plane is like, oh cool, we can see what the things look like. So let's see, we've got x squared plus 3xy. It's funny, I'm looking back there to see that it's literally like in my notes right here. Minus 11x. Ooh, that's not what I want. I can share my screen if you guys want to see it. Obviously, you can also do this on your own, right? You have the capability, I imagine, right? There's either this one or there's the web-based one that I shared with you guys as well. And then the other one is y minus x minus 1, and then 2y minus x plus 1. Okay, let's see what we can. Do I have enough? I want to go bigger on my x-axis here. I want to make x like 7. Okay, cool. So neat, right? And so we know that, let's see. So 0, negative 1/2 is supposed to be a sink. So if I go to 0, negative 1/2, right, things are definitely pointing in towards it. Okay, cool. And we know that 0, 1 is a saddle. So, right, if we try and go towards 0, 1, we definitely get pushed away from it in different ways, depending on if we're coming from the left or the right. We have to come from the right up, or like this way, that way. So, and then we can clearly see we have this spiral sink here, I think, right? Oh no, it's an unstable spiral. Yeah, right. So it's interesting because I think at the beginning I thought my spiral was going inwards, but clearly the arrows show it's pointing outwards. So right, anything we pick around there is going to spiral away. And then lastly, we have another saddle over at 5, 2, at this area over here. It's not getting anything close to it. If we pick things here, we can see, oh yeah, we're definitely saddling here. Okay. So it's, I mean, totally unnecessary, I think, but it's really kind of nice to see, oh yeah, the graph is definitely doing the things that we expect it to be doing based on how we classify our equilibria. So I would highly recommend when you're doing these kind of problems, I think it's worth, if you have the time, to look at p-plane and kind of just see what's happening so that you have a better idea of how to understand what's going on. That's all I've got for today. Next time I imagine we'll probably still talk about this stuff, but we'll probably also start talking about the probability stuff and the combinations and permutation. I imagine Rodriguez might take a little while to still get there, but Rademacher is definitely there, so we should start to talk about it. All right, that's all I got. Let me know if you guys have questions. You can always post a discussion, send me an email, you know the deal. I'll say hang in there. We've only got a few more weeks to go, so I will see you all on Wednesday. Bye.
Thank you.
Thank you.
Welcome, of course. Happy to see you guys.